Welcome back to Chemistry Clubhouse. Today we're going to talk about coffee cup calorimetry. In today's lesson, we're going to learn how to determine the specific heat of an unknown metal. Okay, so let's set up this problem. Right over here, you have a piece of metal. In this case, it's an unknown metal. It weighs 55 grams. So this is 55-gram piece of metal. In the beaker, we have hot water. That hot water is boiling. It is measured to be 98.6 degrees Celsius. What we're going to do is we're going to take this piece of metal and we are going to put it in here and let it heat up. Because the transfer of energy from the hot water goes into the metal, well, the metal will also have a 98.6 degree temperature. Now, over on the right side, over here we have just plain old room temperature water. So we take the temperature of that ends up being 23 degrees Celsius. Also, you take the measurement of the mass, and the mass of this is 125.7 grams. So we've got the mass, we've got its temperature. What we are now going to do is take this piece of metal, now that it's 98.6 degrees, and we are going to put it in here. And we're going to let that equalize out. So this temperature, this temp is its initial. After it equalizes out, the temp final ends up equaling 26.2. So if you notice, the metal went from 98.6 down to 26.2, and the room temperature water went from 23 up to 26.2. Now, how do we figure out the specific heat capacity of this metal? That's the whole goal of this problem. So this is the setup. So let's write down all of our information. So we've got the mass of the metal equals 55 grams. The temp of the metal equals 98.6. The mass of the water equals 125.7 grams. And the temp of the water equals 23 degrees Celsius. After the fact, we end up having a temp final, or the equalized temperature, equals to 26.2 degrees Celsius. So this is the whole setup. We've got everything going on. So we know that this energy, first, we have the energy going from the hot water into the metal, and then the metal is going to release all that energy into the water, and that energy in the water, or the water, is going to heat up, whereas the metal is going to cool down, and eventually they'll get that equilibrium where the temperatures are the same. Okay, so what we need to do is figure out how much energy was released by the metal and how much energy was absorbed by the water. Okay, so we can do very simple. We've got Q of the metal, and we've got Q of the water. So the Q of the metal, using our equation that we already know, we know that it's mc delta T. So again, that's the mass of the metal, that's the specific heat of the metal, which is what we're looking for. This guy is what we're looking for. And then we've got that change in temperature of the metal, which we just established went from 98.6 down to 26.2. The Q for the water is also mc delta T. Well, that mass is the 125.7 grams. The specific heat here, we already know. It's 4.184 joules per gram degree Celsius. That's a number we just know. And then again, the change in temperature is, again, it started at 23 and it went up to 26.2. So now we just got to look at this and go, okay, how do these work together? So we've got this first law of thermodynamics. First law of thermodynamics Oops, that's bad spelling. Dynamics is energy cannot be created or destroyed, only transferred. So in this problem, we know the energy that the metal had is then going to transfer over to the room temperature water. Okay? So, here's the big question. If I have the Q metal and I add that to the Q of the water, what is that going to equal? Well, we know this is going to release or give off energy. And then this guy is going to absorb energy. Well, if the amount of energy released by the metal is being absorbed by the water, well, we know that this guy is going to end up being negative because it's losing its energy, and this guy is going to end up being positive because it's gaining energy. Well, if energy can't be created or destroyed, the energy lost is the same as the energy gained, which means this has to equal 0. So now we can just make a big old equation. So we've got the mass of the metal times the C of the metal times the change in T of what metal, but we're going to flesh that one out. Temperature final minus temperature initial. All right, plus, and then we've got the mass of the water times the C of the water times the temperature final minus the temperature initial equals 0. Now we know from what we just wrote down, we know that the mass of the metal is 55 grams. The C is what we're looking for. We don't know that. Now we can just plug in our temperature final. So in this case, the temperature final is that 26.2. But the temperature initial was that 98.6 because that's where it was. It was in the water bath. So that's 98.6 degrees Celsius. So this is one big math problem. The right side, or the water, the Q for the water is the mass of the water. So in this case, it's 125.7 times the 4.184 joules per gram degrees Celsius. And then in this case, it's 26.2 minus 23, which was the original temperature of the water. And this all equals 0. So now we just have one singular variable in here, and that's that C. So we've got to do a little bit of algebra. If I multiply this entire thing out right here, we get an answer of negative 3982, and we keep that C there. This over here, if we multiply all this together, we end up getting 1682.97, and that is all equal to 0. So now let's just move, we're going to just move this over to here, and now we have a negative and a negative, which means when we divide, we'll end up having C as a positive. So what we end up getting will be C is equal to 0.423 joules per gram degree Celsius. And that is our answer. I hope this was helpful. Again, this is just how to determine the specific heat capacity of an unknown metal. There are other ways of manipulating these same problems. I will show these in another video. Have a good one.